The main bit of homework this week is to study for the midterm. We'll talk more about that in our live section. But in addition, you should do some reading through Algorithms 1.4 and 1.5. That's the last two sections of Chapter 1. And you should also begin to think about a homework problem that will be due the week after the midterm. This homework problem is a variant on a linked list called a doubly linked list. In this case, you'll be implementing a data structure called a doubly ended queue. This is a queue where you can put things on each side and take them off of each side. So it generalizes both queues and stacks. As usual, I've given you a skeleton file for this homework, but unlike previous homeworks, the main method is just a sequence of tests. It's important that you create functions in the order that they're tested so that you can move through this main method elegantly. So that you understand how the queue is supposed to work, I want to walk you through the main method and show you pictures of the state of the machine at each moment. I'm providing these pictures for you as a PDF file, and in addition you can see the main method that I'm using with the line numbers, because in your file the main method probably will move around and may not be in exactly the same line numbers. There's also a zip file here containing images that you can download to your computer if you prefer to look at that instead of the PDF. So let's take a look at the main method. The first line of interest is line 304, where we allocate a double-ended queue object. My main method therefore gets one of these objects. The object has a prescribed structure. It has a first and last pointers and a counter. Your program should manipulate these pointers just as I specify here. On line 305, I'm going to push an element on the left of this queue. And you can see that that puts the element here. Note that this is now both the first and the last element, and that the count is now 1. The item here is 11, and there's nothing either before or after it. It's the only element. After each operation, I run the check method. This method will check that the list is well formed, and in particular, that the number indicated here for n is equal to the number of nodes, and that the first and the last pointers are formed correctly. After we push on the left once, we'll push on the left again, and this is going to put 12 before 11, so 12 becomes the new first. Then we'll put 13 in front of 12. Then we'll start to pop these things off the left. So when I remove things from the left, I get them out in the reverse order that I put them in on the left. So first I'll get out 13, then I'll get out 12, then I will get out the 11. If I push on the right-hand side instead, it behaves the same, except things go at the end instead of the beginning. So when we push the first element, it looks pretty much the same as when I pushed on the left, because here I have one item and it's the only item. It's both on the left and the right. But as I continue to push, you can see the difference. When I pushed 12 on the left, it became my new first element. When I push 12 on the right, it will become my new last element. And so I can continue pushing on the right till I have 3 elements. If I pop from the right, of course, it's again going to behave like a stack because I'm taking from the right. So I'll take first the 13, then the 12, and then finally the 11. Of course, I don't have to separate left and right in this way, and that's what makes the double-ended queue interesting. So what I can do here on line 333 is start pushing on the left and the right in alternation. And when I get that, you'll see I push 11 on the left, then 21 on the right, then 12 on the left, 22 on the right, and then I can start popping off. So in this case, I'm going to pop always on the left. So first I get the 12, then I'm going to get out the 11, then the 21, and then the 22. I can play the same game, alternating left and right, and then pop on the right. And so here I'll push 11 on the left, 21 on the right, and again 12 on the left, 22 on the right. Popping from the right, I'll get 22 first, then 21, then 11, then 12. If I attempt to pop from the queue when it's empty, as it is here, I'll get an exception. And the test here is checking that it is a no such element exception. We'll do that for both sides. So that's push left, push right, pop left, pop right. I recommend that you get everything working on the left and draw the pictures of the state, make sure that everything looks correct, and only after you've gotten the left side completely working, then symmetrically do the code on the right. When you do this, you'll be able to copy your solution from the left and simply make it complementary. So first becomes last, last becomes first, previous becomes next, next becomes previous. Once push and pop are perfect, then you should go on to this next problem, which is concatenation. The idea of concatenation is to put two queues together. It's an asymmetric operation. What's going to happen here is that the queue on the left-hand side of the dot is going to get all of the elements from the right-hand queue, and that queue will be empty. In the case that I'm concatenating two empty queues, well, the result is still an empty queue. And if I have a queue with one element and I concatenate an empty queue to it, well, I still have a queue with one element. For a more interesting example, I need two queues. Let me take them on line 396 to be D1 and D2, and I'll push some elements onto each of these. So we'll push elements on the left of D1 and on the left of D2, and now I have two separate queues. When I concatenate them, D1 will take all of the elements from D2. So D1 will result in 4 elements. And note that D2 now has 0 elements. So this is a destructive concatenation operation. The left-hand side steals all of the nodes from the right. As with push and pop, concatenate can be written without a loop. It's the case analysis which makes this problem challenging, not looping behavior. And so it's really important that you understand what your code is supposed to do before you try to implement it. You may find it really helpful to use the debugger or the trace drawing software with this homework, because in a linked list, things can get confused if the links are all pointing the wrong way. So checking that visually can be very helpful. There's several more tests here involving concatenation, but the most exciting one is on line 424, which takes two queues of length 6 and concatenates them together. The result is D1 will have length 12, and afterwards D2 has length 0. The last problem of the homework does require a loop. It's a delete function, similar to what you've already done for singly linked lists. And this delete function is not only going to remove an element, it's going to return the value that it has removed. So to see a nice example of this, we can look at line 436, where we're going to delete the 0th element of this list with 10 elements. On line 436, we delete the 0 indexed element of the list. We're indexing beginning with first, so what will happen here is we remove this node with item 10 from the list. Also, we'll update k in the main function to be 10, and you can see that that happens here. Note that we have one fewer elements in the list. So on line 438, when I delete the 8th element, I'm now deleting the 8th element of this modified list. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's the last element indeed. Then on line 440, I delete the element with index 4. So that's going to be 0, 1, 2, 3, 4. That'll be the element with item number 15. And indeed, it gets removed. It's important to notice the structure of a properly formed doubly linked list. The way it's coded here, first is a pointer to a node, which then may have a next pointer to a node, and then continuing on, more next pointers, till we get to the end of the list where next will be null. Note that we can also go backwards starting from last. We can use the previous pointer to get back to the beginning. And note that when we get to the first element of the list, previous is null. So as you would expect, the empty list is represented in this format by choosing first and last to be null. Note that the redundant count must be the same as the number of nodes in the list. This homework is challenging for most people, so I suggest you don't wait too long to get started on it.